Hello, Pre-P Chemistry. How are we doing today? Hopefully y'all are doing well. So today we are going to be continuing our notes on thermochemistry in Unit 11. And in this set of notes, we are going to cover the heating curve and specific heat. All right, so let's go ahead and dive on into this. So first off, the heating curve. Now, the heating curve, its purpose is to represent a change versus the energy of a substance. And so basically we're trying to look for a phase change that's occurring as a result of that change in energy. Now, they are going to look like a staircase. And so this is actually what we would see as a heating curve. All right, now, here's a question. Looking at this, do you see a curve anywhere? No, you do not. This is called a heating curve. I like to refer to it as a heating curve, not curve, because there is no curve on the heating curve, right? It is just showing the stair step, these angles, right? Not a curve, these angles that show a phase change occurring, all right? Now, while we're looking at these, we do need to recognize where the phase changes are occurring and where we have just a single state of matter. And so that is what we are seeing right here. Down at the bottom, we know that we've got the least amount of energy, right? And we know that if it's the least amount of energy, that matter is solid. Then it's going to go through a phase change right there. Afterwards, after that phase change, so in the case of going from a solid, we're going to phase change by adding energy to turn into a liquid. That would be melting, right? So our phase change here would be melting. Keep adding energy, and then that is going to turn completely into a liquid. Then we can continue to heat up that liquid until it starts to what? Boil. And so when it starts to boil, again, we're going to see that phase change occur. So boiling is going on right there. And so during that stage, we're going to have a little bit of liquid and some gas. Towards the liquid end, we're going to have more liquid, and towards the gas end, we're going to have more gas. So as we continue to work our way across in this direction towards the right, we're going to see that phase change go more and more and more. And we'll see more and more and more of the that state of matter that we're closest to. So as we get closer to the end where there's very, very small amounts of liquid left in the bottom of, let's say, a pot that's sitting on the stove, right? We're boiling some water there. Eventually, we're going to get to the point where we boil off all the water, and then we are 100% gas. And then that would be when we see that temperature start to rise again, okay? Now, this is a heating curve. In reverse of that, we would have what we would call a cooling curve. And it's basically the same thing as a heating curve, but in the opposite direction. So instead of heating up, we are then going to be cooling down. So we're going to be removing energy, all right? All right. So we need, or y'all need, to be able to identify the parts of a heating curve. So let's go ahead and look at our parts here. So first off, part A. Well, A is this point right here at the corner. And that point is going to represent our melting point. So that would be the melting point. And then over here in this corner would be that would be our melting point. And then in this corner right here would be our freezing point, right? And so if I'm coming in the other direction with a cooling curve, we know that this corner right here would be the freezing point. And this corner right here would be the melting point, okay? So one thing to note about a melting or freezing point is that they are points. They are going to be a temperature that we are looking for, all right? So A represents the melting or freezing point. And then for the purposes of water, which water is kind of one of those common substances that we work with in chemistry, it is 0 degrees Celsius. All right. Now, let's look at point B. All right, so point B is going to represent these corners. So this corner right here would represent boiling, and then this corner right here would represent condensation. That condensation point and that boiling point. So B is boiling and condensation point. And again, remember that it is a point, which means it is representing that single point, that single temperature that we're referring to, okay? That we see that phase change start to occur. And then for boiling and condensation for water, that's going to be 100 degrees Celsius. All right. Now let's look. So the next one we have here is C. C represents temperature, and it's going to be that change in energy, because remember that temperature is the average kinetic energy. So if I'm changing my temperature, I'm going to see that on my y-axis over there on the left. So it represents temperature. And this should be in degrees Celsius, okay? D, right here, it's going to be our x-axis, and D is going to represent either the energy that we're adding or time, okay? And so, because sometimes we might not be adding energy. For instance, if I'm causing something to cool down, sometimes it's just a matter of time, waiting. And so D, that x-axis, can represent time or energy. All right. Next we have E. And so E is representing this line right here. So looking at that line, we've got the least amount of energy at the lowest temperature. And so lowest temperature, lowest energy, that would tell us that that is the state of matter being a solid. Now, if we're talking about a heating curve, which we see right here, this is going to be the solid being heated. Okay? If it were a cooling curve, then it would be the solid being cooled. All right? Now, in this is 100% solid. You will not find any liquid. You will not find any gas. It is all solid during that phase. All right? Next is F. Now, if you look at this, it does have a direction that F is going. F is going from the left to the right, from the solid to whatever is going on here at H. So if I'm going from solid to whatever's going on at H, that would be what we call melting. Now, in melting, it is not going to be 100% a state of matter. Why? Because when we're melting, we're going to have, for instance, with water, we're going to convert from a solid to a liquid. We know that ice does not immediately melt all at once, right? It takes time for that ice to completely melt. And so we see that phase change occur over a period of time, right? As we're adding energy, as it's absorbing energy, okay? And so, for example, again, I said this earlier, but on this end right here, we would see more solid, versus this end down here, we would see more liquid, okay? And so during that phase change, we would call that melting. Now, G represents the other direction. So in this case, we're going from H over here to the solid. So we're going in the opposite direction. And so that would tell us that that is freezing. All right. So then if we know we've got melting and freezing, those phase changes, then what would H represent? Well, it would represent being a liquid. And again, with it being a heating curve, this is being heated. If I turn that curve around and it turns into a cooling curve, then it would be the liquid being cooled. And again, on those slants, anytime you've got any of these slants, that is 100% that state of matter. So if I'm talking about a liquid for H, it is 100% liquid. There is no solid, there is no gas. It is all liquid. Next, I have I. I represents another phase change. So again, we have passed a solid. We're currently at liquid, but now we're trying to go past liquid. We know that if I add or continue to add more energy to a liquid, what happens? Well, the phase change begins to occur. It starts to turn into a gas. What do we call that? Well, we call that boiling. And in chemistry, you might hear it vaporizing. It's turning into a vapor. Now again, remember that any of those flat places, any of these kind of horizontal areas on our graph, those represent a phase change. And we know that we are not 100% any state of matter. We're going to be a mixture of the one that comes before and the one that comes after. All right. Next, I have J. J is going in the opposite direction of boiling. Well, in terms of going from a gas to a liquid, what we would call that would be condensation or condensing. All right. Very last one I have here is K. Well, K represents that area where we have passed condensing we've left boiling. And so now we are in this new state of matter, which we know after liquid, things turn into a gas. So K represents the gas. And again, being a heating curve, it is going to be being heated. All right, and that is important that you recognize if we're adding energy or if we're removing energy, it is based off of the direction of our curve. Okay. So some other things to note on here. On your horizontals, our kinetic energy is going to stay the same. But our potential energy is going to either increase or decrease depending on if I'm a heating or a cooling curve. So for the purposes of this curve, we are going to have a potential energy increasing as we're moving from left to right. On my slants, that's going to be where our kinetic energy is increasing, but our potential energy is staying the same. All right. Now remember that temperature just represents the average kinetic energy. And so if temperature represents the average of the kinetic energy, then it's directly related to kinetic energy, right? So as I increase my temperature over here with C, as it increases the temperature right here, we're going to see that change in kinetic energy. But if you notice on these horizontal areas, we're not actually changing our temperature, right? Well, that tells me that the kinetic energy is going to be staying the same, right? Okay, so that would be a heating curve. So now let's take a look at specific heat. So with specific heat calculations, we have one formula that we use. That formula is Q equals MC delta T. I have always read it as Q equals MCAT because I feel like that delta, that triangle, represents that A in CAT. So Q equals MCAT. Now, what do those symbols represent? Well, Q represents the heat, and that's either going to be in joules or calories. It does depend on what specific heat that we're actually using. Mass, or M, represents mass, and that does need to be in grams. Why? Because your specific heat is in grams, okay? C represents the specific heat, and that typically is going to be in joules per gram degrees Celsius. Specific heat is going to be one of the important ones that you keep an eye on your units, because it's going to determine what other units you need to use throughout your equation. Okay, so if my specific heat ends up being in grams, but my mass is in kilograms, I know that I am going to have to convert that mass into grams so that it works with my specific heat. All right, same thing with joules. If I'm in joules here, or with my specific heat, which again, traditionally I am, then what that tells me is that my heat that I'm either given or solving for should also be in joules. Now, if the question asks me to solve for calories, I would need to make a conversion. If they ask me to solve for kilojoules, again, I would need to make a conversion. So keep an eye out for your units, because those are something that can change throughout these. Okay. The last thing is the delta T, that change in temperature. Now remember, I told y'all when you're solving for your change in temperature, it is final minus initial. So final minus initial, and that should also be in degrees Celsius. Again, why? Because specific heat is in degrees Celsius, and so we do need to keep our units consistent. So looking at this, it says a sample of water is used to absorb energy released when a compound is burned. The following data is collected. So what they tell us is that we've got a mass of water of 50 grams. The initial temperature of water was negative 15 degrees Celsius, and the final temperature of water was 128 degrees Celsius. And they ask us, what is the change in enthalpy for this data? Well, here's the thing. Different states of matter have different specific heats. And so looking at this, I'm talking about water, and I started at negative 15 degrees Celsius. Well, at negative 15 degrees Celsius, water is a solid, right? Because at 0 degrees Celsius, is where it turns into a solid. And then we know that water as a liquid is going to undergo a phase change at 0 degrees Celsius. So this is 100% solid from negative 15 to 0 degrees Celsius. But it says we go up to 128 degrees. Well, we know that water stays a liquid until it hits 100 degrees Celsius. But at that point, it undergoes a phase change. And then from there, it turns into a gas, and then it would continue to increase in temperature after that at 100 until it reaches 128 degrees. So looking at this, I've got a state of matter, specific heat is different than the specific heat here than the specific heat here. And so we have to solve multiple times. We're going to have to solve for the specific heat. On top of that, we know that looking back at our heating curve here, we know that during a phase change, energy is still being added. And so we also have to account for that energy. So there is an additional formula that's going to work in between those in between those different states of matter. All right. And so I'm going to go through all of that. I'm going to show y'all how to do that. But with specific heat, really it's just coming down to Q equals MC delta T and seeing what's actually going on with these equations. All right. So what state of matter is water at negative 15 degrees? Well, it is a solid. And at 128 degrees, it is a gas. And so we know that we've undergone two different phase changes, first from solid to liquid, and then from liquid to gas. My suggestion with a specific heat problem is you draw a heating curve. And so I know that I start off as a solid, and then it undergoes a phase change, and then I know that it's going to continue up and go until it's a liquid, and then I know there's another phase change, and then it's going to continue up and it's going to be a gas. I'm going to end right there at 128, and I'm going to start at negative 15. And so when I'm looking at that, that shows me, okay, I'm going to have to solve for this step, this step, this step, this step, and that step. And so it kind of helps us kind of label or recognize whatever things that we need to solve for when we're doing these problems, okay? So You know from math that the same equation can't be used to find for the slope or the flat line, and so we do have two different equations. Really, they come down to they are the same, but they've just kind of converted it a little bit. So Q equals MC delta T. That's going to represent all of our slopes. Flat lines represent Q equals M delta H. So this is telling us the change in energy, and this is changing us the change in temperature. So basically, we're just looking at two different things here. We know that delta H is essentially representing that potential energy, whereas that delta T is representing the kinetic energy. And so that's all we're doing is seeing how that changes. Now, looking at our problem that we had before. So this is the data they gave us. So the mass of water was 50 grams, the initial temperature of water was negative 15 degrees Celsius, and the final temperature was 128. So I started here at negative 15, okay, on my heating curve. And I continued until I hit 0 degrees. And that is all solid, okay? But once I hit 0 degrees and I continued to add energy, now I'm going to start to convert from a solid to a liquid. So I'm undergoing that phase change. So step 2 here, I underwent the phase change. And I know that if it's a phase change or one of the flat lines, one of the horizontal lines, I use the M delta H. Now, anytime I see a change in temperature, I'll use the delta T, right? So Q equals MC delta T. Now, looking here, we continued to heat the substance, continued to add energy until eventually we reached 100 degrees Celsius, and that would be where it is a liquid. At that point, once we're at 100 degrees Celsius, then we're going to see that phase change occur. So we're going to see boiling start to happen, and that water is going to start to turn into a gas until we eventually have 100% gas until we reach the 128 degrees up there at the top for the gas. So basically what I'm going to have to do is calculate each of those steps. Now, y'all, this is going to be the longest problem that you will see. You typically will have like one phase change that occurs. So you're not typically going to have to actually see or work through a bunch of steps like this, 5 different steps. But the idea behind this is so that y'all can see the entire problem in the biggest scenario that you could possibly see it in. All right, so very first step, step 1. At step 1, we are solid, but we're going to be changing our temperature. So anytime we've got a change in temperature, we're going to use Q equals MC delta T. So then Q equals my mass, which was 50, times my specific heat. So the specific heat of water as a solid is 2.11. So 2.11 joules per gram degrees Celsius. Now, grams is on top here, it's on bottom here, so that is going to cancel out. Then I've got my delta T. Delta T represents the change in temperature. Change in temperature is final temperature minus initial. My final temperature as a solid is 0 degrees Celsius. My initial temperature is negative 15. So final minus the initial, negative 15 degrees Celsius. These Celsius cancel out that Celsius. So I take that, I plug that into my calculator, and I find that Q equals 1,580 joules. All right, step 1's done. Step 2. Now, in this case, I don't see a change in temperature, so I use Q equals M delta H. So then Q equals, again, it's 50 grams of water. Now, I need my delta H. So delta H, which is heat of fusion. Heat of fusion represents if I'm going through melting or freezing. Heat of vaporization represents if I'm going through boiling or condensation. So with heat of fusion, I found that the heat of fusion is in kilojoules per mole or kilojoules per gram. Now, in this case, I've got a mass in grams, right? If they told me moles, then I could use the moles formula. but they've got grams, so I'm going to use that 0.33. So there's 0.33 joules per kilojoules per gram. All right. Again, I cancel out those grams because I'm going to be left with kilojoules. So I plug that into my calculator and I find that my Q equals 16.5 kilojoules. Now, my step 1 and step 2 are in 2 different units of energy. I'm going to go ahead and convert this into joules, which, remember that kilojoules to joules, there's 1,000 joules per 1 kilojoule. So that's going to take and move that decimal over 3 times. So we get 16,500 joules. Done with that step, done with that phase change. Now I'm in step 3. So looking up here at step 3, I'm 100% liquid. I am seeing a change in temperature. So I'm going to use Q equals mc delta T. So then my Q equals my mass, 50, times my C. Now the specific heat for liquid water is 4.18. So I have 4.18 joules per gram degree Celsius. Okay. And then temperature. Now, in this case, final minus initial. My final temperature in a liquid water is 100 degrees Celsius. Because after that point, it's all gas, right? Before that point, it is going to be liquid. Minus the initial temperature. Well, in this case, the initial temperature was 0. Because lower than 0 degrees Celsius, it would be a solid. Okay. So I plug that into my calculator and I find that Q equals 20,900 joules. Now I'm in step 4. Step 4 is, again, no temperature change. We've got a phase change occurring. So Q equals M delta H. So then my Q equals my mass, 50 grams, times my delta H. So coming back up here, this is for boiling or condensation. So I use my heat of vaporization. Again, I've got a mass, so I'm going to use that 2.26. So there's 2.26 kilojoules per gram. Cancel out my grams. I plug that into my calculator and I find that I have 113 kilojoules. Again, we need to be consistent with our units, so we're going to convert this into joules, which is 113,000 joules. Still not done because I do need to show that final change in temperature, so I'm going to come back up here, and I'm going to have step 5 right there. Now, step 5, I do have a change in temperature again, so Q equals mc delta T. So then my Q equals 50 times my specific heat of a gas for water, which is 2.08 joules per gram degree Celsius, times my change in temperature. So my final temperature here is 128, and my initial temperature is minus 100 degrees Celsius. So then I plug that into my calculator and I find that Q equals 2,910 joules. Okay. So now I've solved 5 different things, but that doesn't tell me the amount of energy that required. So now all I need to do is take all of my energies from each of those different phases and solve for the total. So I had 1,580 plus 16,500 plus 20,900 plus 113,000 and plus 2,910. So this represented step 1, step 2, step 3, step 4, and step 5. Add all those together and I found 1 0.54890 joules would be my final answer there for our energy. So basically 155,000 joules required to heat water from negative 15 degrees Celsius all the way up to 128 degrees Celsius. All right? And so, like I said, that is the most difficult way that you could see these heating curve problems with specific heat. So let's take a look at this next problem. What I want y'all to do is go ahead and give this a try. Now, do recognize that not all of these are going to have a phase change. So sometimes you might just need to use Q equals MC delta T, or you might just need to use a phase change, and that's it, all right? And so that Q equals M delta H. So looking at these, always take a look at your temperatures and see how that's changing and see what's going on with that phase with whatever substance you're working with. With water, remember, freezing is 0 and below. Liquid is 0 to 100 degrees Celsius, and then gas is above 100 degrees Celsius, okay? So go ahead and give this next problem a solve, and then, so pause your video, and then we will quickly talk about it. All right, so here's what you should have done. First off, you should have recognized that going from negative 15 degrees Celsius to negative 2 degrees Celsius is a solid. It stays a solid. There is no phase change that occurs. And so all I need to do is Q equals MC delta T. Q equals MCAT. I plug in my numbers, so I found my mass to be 15.5. The specific heat as a solid is 2.03 joules per gram degree Celsius. And then I did final minus initial, negative 2 minus negative 15. Plugged that into my calculator, and I found 409.045. Then I used my sig figs, and I found that my answer was 409. All right, y'all, so that is it for our notes on specific heat and heating curves. As always, let us know if you have any questions. I'm going to leave the rest of this for y'all to do as practice. You can always check the key later. But let us know if you need anything, and have a great rest of the day. Bye, y'all.